Hello everyone, welcome to Curiosity Beyond Edge. Here I'm running a particle-based population simulation. We start with two identical groups, Group A and Group B, shown in red and blue. Both groups begin with the same population size, so neither has an initial advantage. Each particle represents an individual with a life cycle. A particle has a minimum reproduction age, which is the time that must pass before it can reproduce, and a maximum age, which is when it dies. For this run, the parameters are initial population of 35 particles per group, minimum reproduction age of 1, maximum age of 10, offspring per reproduction event of 1. Because the simulation contains randomness elements, I will run the experiment 3 separate times with the exact same parameters. This helps verify that the outcome is not simply caused by randomness, but reflects the behavior of the system itself. Let's start it. After running the simulation 3 times, the outcomes were mixed. In 2 runs, the blue population dominated, while in 1 run, the red population prevailed. Because the starting parameters were exactly the same, this variation indicates that stochastics effects, the randomness in interactions and reproduction timing, can influence which group eventually dominates. From this small set of trials, there is no clear deterministic advantage for either group. The results suggest that under these symmetric conditions, the system dynamics allow either population to win, depending on how random events unfold during the simulation. To draw stronger conclusions, a larger number of runs would be needed to see whether a consistent statistical bias emerges. For the next part of the simulation, I'm changing one parameter for Group B. Specifically, I'm increasing the minimum reproduction age from 1 to 2. This means that the particles in Group B now have to wait 2 seconds after they are created before they can reproduce. At the start of the simulation, this creates a short period where Group B cannot reproduce at all, even if particles collide or interact. During that same time, Group A is already able to reproduce because its minimum age is still set to 1. Theoretically, this should give Group A an advantage since it has a higher chance to reproduce earlier and increase its population before Group B becomes active. Now let's run the simulation and see whether this delay actually causes Group A to become dominant or whether randomness in the system still plays a major role. Across all three rounds, the red group consistently won. That suggests the earlier reproduction time gave them a strong advantage even with randomness in the system. Now let's change the dynamic again. I'm going to reduce the maximum age of the red particles. So the reds will still start reproducing earlier, but they will also die sooner. On the other hand, the blue group starts reproducing later, but they live longer. Let's run the simulation again and see which strategy works better. In this configuration, something unexpected happened. In all three rounds, both populations eventually died out. Neither group was able to sustain itself over time. The red group reproduced earlier but died sooner, while the blue group reproduced later but lived longer. Apparently, that balance pushed the system into a situation where the overall population could not maintain growth. Alright, I'm returning the maximum age of group A, the red particles, back to 10. This means the red group will still reproduce earlier, but now they will also live longer again. Let's run the simulation and see whether this restores the advantage for the red group. As we can see, once the maximum age of the red group was returned to 10, the pattern came back. The red population becomes dominant again. Now let's explore another scenario. This time, I'm going to reduce the initial number of group B particles to 20, making them a minority at the start of the simulation. Group A will keep the larger population. Let's run the simulation and see how starting as a minority affects the population dynamics. As we can see, in all three rounds, the red population dominates. That makes sense because Group B starts smaller, and having fewer individuals at the beginning naturally reduces the chance to compete and grow. This shows how initial population size can strongly influence the outcome. Now let's change another parameter. I'm going to increase the number of offspring for Group B so that each particle produces 2 offspring instead of 1. This gives Group B a reproductive advantage even though they start with half the population of Group A. Let's run the simulation and see how this change affects the population dynamics and whether the minority group can catch up. In all three rounds, Group A still dominates, even though Group B started with half the population and each particle now produces 2 offspring. It still wasn't enough for them to compete effectively. The red group's early start continues to give them a strong advantage. Next, I'm going to increase the minimum reproduction age for Group A to 2. This means they have to wait 2 seconds before they can start reproducing. Let's run the simulation and see whether this delay changes the outcome. As you can see, the delay in reproduction for Group A allows Group B to take over, even though it started with only half the population. During the later part of the simulation, you might notice the animation slows down a bit. That's just my laptop starting to lag, which causes some delays in the simulation. Next, I'm going to reduce the initial population of Group B to 15 and see how that affects the outcome. What do you think will happen? Let's run it and find out. These results are really interesting. In the first round, the minority group B, which has higher number of offspring and a minimum reproduction age of 1, was able to take the lead. In the second round, however, both groups went extinct and died out completely. In the third round, Group A became dominant again. This shows that in this particular configuration, the outcome is highly sensitive to the initial position of the particles and the randomness in the system, leading to three completely different results even with the same parameters. In reality, the number of groups and interactions between them are far more complex than what we have explored in this basic simulation. Thank you so much for watching. If you enjoyed this video, like and subscribe for more content like this on Curiosity Beyond Edge channel. And if you have any special ideas or variations you would like to see in this simulation, please comment below. I would love to try them out in the future videos. Thank you.